education, the only education that matters. Can you hear me properly? Because today I'm a bit low. My voice is low.
Yeah, I can hear
Can
you.
you hear me now? Okay. Let's start with this one and let me download. I don't know if you guys can zoom in there, right?
Mm.
Yeah.
Oh, here's the question. Uh, yeah, let me try to print it. If it's gonna look nice, yeah, it's better. So yeah, like I said I'll get information from the lecturer. The lecturer is not around. He's not around campus. I think he's gonna come back tomorrow, from what I've heard. So this is a vertical system. I'm pretty sure you guys can see what is happening here. And where is the pivot? So first thing to do, Angele, is what is the question saying? Consider a uniform rigid bar of mass m, length L, pivoted at one end and connected symmetrically by two springs other end as shown in figure 1. It is assumed that the springs are unstretched when the bar is vertical. Now, what are they saying? Mm, oh, God. I'm tired. Andile. Okatset. Kikatset.
I'm also tired.
Yeah, but let's do it. We have to do it. People has to do it, and it is us. Okay, the first thing to do here, guys, we need to draw what is called the free body diagram. The system here is vertical. So what does it mean? It means the law that we say that weight cancel, static equilibrium, what, that cannot be applied here because we have a vertical system. So what do we do from here? Derive the equation of motion of a system for small angular displacement of the bar, what. So this is what's happening. First of all, you need to identify in this system here, where is the pivot? The pivot is at the bottom. Do you see it?
Mm.
So now, what do we do? You saying, Andre?
Nothing.
I thought you said why is it at the bottom.
No.
I was about to say I don't know. Now, basically, yeah, I think I'll use the ruler for more accuracy. Miss Androsi.
Yes, sir.
Grant. I don't know, Andile. I've received a request saying that the video that I post, I should be recording them alone so that they will be clean on my YouTube channel and so on. So it's winning, let's say, the quality of my YouTube videos. But yeah, that's what makes me me, so I think I'll leave it like that for now. So okay, what I'm showing you here, guys, we have this here is just the axis when it is here. Now, as this thing has been shifted to the angle, what does it mean? It means that you have given it a positive direction going through this way. Are we together?
Mm.
Now, what happened, Angele? What are the forces that's gonna be that we see here? What are we gonna have, Angele? How many forces do we see here? We have two springs and we have the weight. So first of all, at the center of this thing, we'll have the presence of the weight. What's going on? Why is it zooming like that? We'll have the presence of the weight acting at the middle here, somewhere here. Are we together, guys? On this one.
Yes.
We will have the weight acting down. We have spring 1, and we also have spring 2. Do you understand why am I writing spring 1 and spring 2 in those directions, guys?
Yes.
Mr. Ndlozi the elephant? No, Ndlovu is the elephant. Mr. Ndlozi.
Yes, I see. I understand.
Yeah, so we move to an angle of theta here. Now, what is important, guys, in this scenario here, because the pivot is down, you will notice that the weight is going the same direction as the direction chosen. So our weight will be positive in this case. Are we together?
Yes.
Yes.
Oh, yes. Now, what do we do, guys? We know the step. What do? We go again. Sum of all the moment about the prevent port O, which is this one down here, of all the external force is equal to moment of inertia of the system multiplied by theta dot dot. Are we together on that one? So what are the forces that we have here, Andile? We do have moment of spring, let me call it Fs1, plus moment of spring, let me call it Fs2, plus moment of the weight. Do we see it, guys?
Yes.
Any question?
No question.
Now, what do we do from here? We know the weight is opposing, so you're going to have minus Fs1 multiplied by, what's the perpendicular distance? They call this distance here to be L. The total distance there is L. So it's gonna be L minus Fs2 multiplied by L as well. Now, how about the weight? Andile, do we have an idea?
It's going to be mm, the weight is empty mass.
Yeah, the weight is mg, but the weight is creating a moment, but with what?
With respect to that distance
The weight
from
in this case is creating the moment is creating the perpendicular distance with the previous axis line. This one. Do you see it?
yeah.
So we can call this distance here to be r. So basically we have plus mg multiplied by r. So how do we solve for r? We can see this one makes a right angle triangle. So what we have is, you know that sine theta, if you use this right angle triangle like this, it will give you what? R over the hypotenuse. So what is the hypotenuse? Remember, the weight is acting at the center of the bar, which is at distance L over 2. It's because the picture is blurry. So that's the reason why the length here will be L over 2, the hypotenuse. So what will there be R? R will be L over 2 sine theta. So for small oscillation, sine theta equivalent to theta. So R is L over 2 theta. Are we together, guys?
Yeah.
So, Angela, you saying yeah because you are tired of me?
I'm with you. I'm with you.
Okay. Glad you are with me, Andile. Now, what is next, Andile? What is fs? We know this thing is a repetition, this chapter here. Fs is k times x, right? So what is the x here? X is r theta. Now, what is r? R is simply the distance where the spring is to the pivot, which is L. That's why you will see here x will be L theta. Remember guys, if you zoom here, this k and this k is the same, so it means people are texting. Who's texting? I hear them. Please don't forget to add me on the group. Okay. Andile. Now, anyway, guys. Okay, let me not shout. Last time I was shouting. Now, what are we gonna have? We're going to have k x. X is L theta, so it's gonna be L square theta. L times L square minus k again, L times L square theta as well, to be plus mg L over 2 theta. Are we together on this one? This is all the moment. Are we together, guys?
Yes.
What
Yes.
we have here as answer is the sum of the force of all the moment. Now, what is moment of inertia, Andile? To get the moment of inertia, guys, we simply identify all the masses. How many masses do we have on this problem? We only have the rigid bar mass. Do we see it?
Yeah.
Okay, so it means we only have the bar. So what would be the moment of inertia here? Remember, guys, center of gravity of the bar is here. Center of gravity, the pivot point is here. So these two lines are parallel. So what do we have, Andile?
You mean the whole?
We have parallel theorem.
It's going to be ml squared divided by 12 plus ml squared divided.
Yeah,
By
Mr.
12.
Ambrosi, are you with me on that one?
Yes, sir, I can see.
Yes. Okay, what's happening also, there is a formula that has been proven that if you have a rigid rod and the pivot is at the edge, the formula simply says that it is 1 over 3 ml square. You can actually prove it by doing the parallel theorem. But if you do have a bar or whatever, a rigid rod where the pivot is here, definitely it is 1 over 3. Are we together?
Yes.
Now, what do we need to do? We have everything, so we can equate them to find the equation. We have minus k L square theta minus k L square. I don't know, I think tomorrow when we meet, I'm thinking we should start maybe chapter 2. Meanwhile, waiting for the lecturer to emphasize on this chapter 1 which type of question to. I don't know, I was suggesting that you can tell me, or we can keep on doing problem on chapter 1.
Chapter 2 is fine for me.
Oh, it's fine for you, ne? Yeah, Andile?
Yeah, it's fine.
Like we can do it.
Oh, like fine to do. Oh, I thought fine like you chow it already.
I've got a problem on chapter 2.
Oh, okay. You see, that's why we have to communicate, because I misunderstood. Now, what is happening here? This k here are the same in this case, so you can make them together. You have minus 2k L square theta plus mg L over 2 theta to be equal to is theta dot dot. Now what is happening here, guys? What do we do when the system is there's no external force applied? Everything should be equal to 0. So what do we have here? We have so we have to bring everything on the same side. So we'll have is theta dot dot. As this move there is gonna become positive. It's gonna become positive 2k L square. This one is going to become negative. I don't know if you see it. Everything theta to be equal to 0. So we make sure that this guy is alone, theta dot is alone. 2k L square minus mg L over 2 is theta to be equal to 0. So this expression here represent Wn square, and guys, as you can see, we are getting used to these fingers. It's not that difficult, ne? Is it, Andile? Mr. Lozi. Now what do we do from here? What is the question saying? We got the equation. They said calculate the mass of the rigid bar. Okay, how do we get that mass, guys? We need Wn. Do you agree, Andile?
Yeah.
If you take Wn square to be equal to 2kl square minus mg L over 2 divided by is. What is is? Moment of inertia, we can write it as 1 over 3 ml square. So we are looking for m. Do we have Wn? I think we were given the information here. They said Fn is equal to 1,3 hertz. Remember, Fn is equal to Wn over what? 2 pi. This one is the frequency. This one is the natural frequency. Are we good on that one?
Yeah, boy.
So we can get Fwn from here. Simply going to be 2 pi multiplied by Fn, and you are done. Are we together? I'm coming now.
Yes, yes.
Okay, and now what is now is just a matter of making m subject of the formula here, so we can do the math quickly. Ne? We can just cross multiply here. We're going to have 1 over 3 ml square multiplied by Wn square, sorry, to be equal to 2kl square minus mgl over 2. So since you want m, you can bring the expression with m on the other side here. So you will have 1 over 3. Let me try to write it properly this time. ml square wn square plus mgl over 2 to be equal to 2k l square. So we can take m as common factor, so we'll have 1 over 3 remaining wn square plus no, m is no longer there. Do you see it? Plus g l over 2 to be equal to 2k l square. So if you can make m subject of the formula, we've got 2k l square divided by 1 over 3 wn square plus gl over 2. This is what gives you m. Any question?
No.
Adila, are you sure?
Yeah, I'm sure.
Mr. Ndlozi?
Yes, sir, it's fine. We can move on to the next one.
Okay, what is the next one again? I think if I check and delay, if I close here, hey, what did I do here? Download. My laptop has more pictures of my classes than my own pictures. Okay, my brother, you can move this up. This is the new deal. Okay, Andile, Mr. Mauzi, what are they saying here? They are saying that a single pendulum is pivoted at O, is controlled by a spring as shown in figure 1. Now, figure 1, the disk of M and D is placed on this released. Derive the differential equation of the motion, and the rod of the mass rod is negligible. So what do we do? Let me try to draw the free body diagram first. Free body diagram. Hey, winter is coming, ne?
Yeah, that's it.
Winter. Technology. Hey, what's happening? Oh, don't tell me that it's restarting. Can you still see my screen, guys?
Yes.
I think I got a network issue here. Can you hear the generator playing?
No.
Oh,
No.
then that's fine. Oh, it means I have to redraw what I was drawing and delay this network. It wants me to work double. 2 shifts. Mr. Ndlozi, are you doing InServe, my brother?
Yes, we couldn't do it at the same place.
Oh, so she's the one who plugged you here, or you knew about?
Yes, she is the one.
Oh, that's why you guys were talking nicely. I'm like, oh, Andile, thank you then.
We're players.
Thank you. Personally, I thought maybe you. Oh, Andile, thank you. Yeah, this is perfect. This is perfect and delay. Now, free body diagram, what do we have, my guys? I'm just trying to draw it nice so that you can have something, you know, that makes sense. That is clean. I know I'm doing too much now. I think I'm cooking too much. Yeah, it's fine. Oh, this free body diagram looks so nice. Okay, my guys, literally what does this mean? That the direction chosen as positive is what? Is this one. Ooh, I think I'm making a mistake here. I'm not sure if I can move this. Yeah, technology. Yeah, do you see why I'm doing it like this, guys? Because the figure is actually showing it the way it is, like that. And they call the distance where the spring is to the pivot to be A, and the distance of the rod to be L. So are we together, guys?
Yeah, I understand.
Andila, you are tired, Andila. How is okay? As it seems like today was a long day at work. It seems like today was a long day at work.
Not really. I have flu, yo.
Okay, what do we do here, Andile? Let's read the question. A simple pendulum of O pivoted at O has the mass and diameter. They said the disk of mass. So do you agree this one is a disk, right, Andile? So if there is a disk, it means this distance here, there's a radius. Do you agree?
Yeah.
Now they said write down the differential equation. Normally on the free body diagram we can also show the tension of the cord, but it doesn't really matter, because if you try to get the moment of this force, it is actually acting straight where the pivot is 0. That's one of the reasons why I'm not including it. It's not really necessary. Are you with me on that one?
Yes.
Yeah.
So now what do we do? Okay, here we go. We have some of the moment about the pivot of all the external force to be equal to moment of inertia of the system multiplied by the angular acceleration. So what are the forces here? We have the spring force opposing here. We've got the weight as well here. These are the two forces. We can include the tension as 3, as I said, is not that necessary. These are the two that we'll be using. So what is the sum of all the moment of all the forces? You have moment of spring force plus moment of the weight. Now, what do we do? Now, as we write like this, we can consider the sign. We know that the spring force always opposes. Do you agree? If I can write, Mr. Bubakar, if I can write minus kx multiply by A, because guys, moment is force times perpendicular distance. The force is acting here. The perpendicular distance is the distance A. That's why I'm writing minus kx times A, because we know force of the spring is k multiplied by x. Are we good on that one?
Yeah.
Okay, and now in this case, if this is the positive direction chosen, so at which direction the weight is going? The weight is going down, so the weight is opposing. So we definitely know that we're going to have a minus mg multiplied by r. Just like in the previous example, weight is creating a perpendicular distance with the initial axis here, which we are calling r. I believe you see it right on the left. Now let's look at something here. If you go sine theta here, what is the opposite side? R. What is the hypotenuse? It is L. L is from here to here, plus the radius. So to avoid confusion, I will call this R here big R, so that you can see what we mean. So what is big R? Big R is L plus R multiplied by sine theta. And we know for small oscillation, sine theta is theta. So we have L plus R, everything multiplied by what? Theta. Are we together?
Yes.
Now, what does it mean? If we have to change this one, remember again here, x is r theta. Are we together? R is simply the distance that is creating the moment here, which is a. So in this case, it will be a multiplied by theta. So we're gonna get minus k a square theta. I hope it's making sense. This a times a will give a square minus m g l plus r, everything theta. Now we are done with the moment. Can we solve for the moment of inertia? Yes, we can. Moment of inertia, what we need to do here is how many masses do we have on this system? We only have the mass of the disk. Do you agree, Mr. Ngozi and Gile?
Yes.
Do not agree?
We agree.
Now, here we go. What do? We have to look for moment of inertia of the disk. What is moment of inertia of the disk? It is half mass radius of the disk square. Now, what is the problem? The disk is located here. The pivot point is here. So definitely we have parallel lines. These two lines will create what? Parallel axis. So because of that, we have parallel theorem. So we'll have to recall again mass of the disk. Now the distance is from the center of gravity of the disk to the pivot square, which is L from here to here, and then radius. Any question, my good people? What's happening? Any question?
No question.
Okay, what do we have? We can equate them to get the to be equal to moment of inertia of the system multiplied by theta dot dot. You know the drill, my guys. What do? We make everything to be equal to 0. So I'll be having is theta dot dot plus, I can write k a square minus mg l. This is l plus r, everything like this by theta to be equal to 0. So we've got theta dot dot plus k square minus mgl plus r over is theta to be equal to 0. Are we together? Any question?
No.
And what was the question saying even here? The question said write down the differential equation of the system. Yeah, that's what we've done. Number 9.2, they said if the mass is 1 kg and damping factor is this, determine the expression for the natural frequency of the vibration, neglect the mass of the rod, which is. So basically what we need to do there, since we've got now the mass to be 1, simply what we're going to do, remember this expression here gives us the natural frequency. So if we have to express natural frequency, simply what we have to do, we have to solve for Wn. What is the root of Ka square minus mg L plus R, everything over moment of inertia of the system? What is it? It is 1 over 2 m r square plus m L plus R square. Sorry. Now remember guys, they said if m equal 1, they want you to get this expression. So what does it mean, Andile? If you substitute m by 1, what will remain in this expression, guys? What do you think will remain, Andile? Ish. This technology, Control C. Okay, yeah, this is what I wanted to do. Let me move it here like this and delete this one. Andile, if you substitute this m by 1, what you'll have is the expression m will disappear. This is the expression that you will simply have. Now you have solved for number 2. If you remember there, you are also given what is called the damping factor. Normally when we have the damping factor, we are in the need of a damper, but in this case, they just gave us the value. There's a reason for it. So what is the damping factor? Damping factor E 0,0247. Oh, got it. 0,0247. I guess that's the right thing. Yeah. Now, Andile, now we can move to 9.3. 9.3, they said determine the logarithm decrement and the amplitude after 3 cycles. Okay. Let's start first with the logarithm decrement. Remember I said when you reach this part where you have damping factors, what all you need to remember are the formulas. And you've got a list of formulas even during your test 1 as formula sheet. I'm pretty sure you know that zeta here is equal to logarithm decrement root of 4 pi square plus logarithm decrement. So basically what we'll be doing here is, we have to solve what we'll be doing here, we have to solve for logarithm decrement. So how do we solve for logarithm decrement? Simply by making it square, but the formula simply becomes like this. If you work it around, logarithm decrement is 2 pi zeta over 1 minus zeta square. I think so. Yes. This is all you need to remember, how to get the logarithm decrement. But if we can prove it, quickly. We can do it, right? So you will have zeta, excuse my zeta, I don't know how to write it, plus logarithm decrement. Is it logarithm decrement square? I'm not really sure inside here. I think there's a square. Anile, can you check the formula sheet? There's this formula there. What is it? Is it logarithm decrement like this or logarithm decrement square?
Square.
Okay. So there's a square inside here, né? To be equal to logarithm decrement this side. So what do? We square all side. It is 4 pi square plus logarithm decrement square like this. This side will give logarithm decrement square. So what do? We can multiply everywhere by this. To be 4 pi square plus logarithm decrement square multiplied by this zeta to be equal to logarithm decrement square. Remember, what we need is logarithm decrement. So what do we need to do to get the logarithm decrement? This one here should move on the other side here. So if we do that, we'll have logarithm decrement square minus logarithm decrement square zeta to be equal to 4 pi square zeta. Now you can take logarithm decrement as common factor square, which is 1 minus this, to be equal to 4 pi square zeta. Zeta should be square here because everything is square. Now what is happening? You want logarithm decrement, so it will be logarithm decrement is square here. It will be 4 pi square zeta square over 1 minus zeta. So definitely logarithm decrement will be the root of 4 pi square zeta square over 1 minus zeta. So remember, the root on top here will come as 2 pi zeta, and here you have 1 root of 1 minus zeta. So this is what is happening right now in delay. I hope I did not make any mistake somewhere. This one is square. Yeah, so it's square here. Square. So guys, you don't really have to prove it. All you can do is to remember the formula. Are we together? Andile, what's happening? Are you with me?
Yes.
Oh, yeah, we have 15 more minutes. We can finish this in 15 minutes. So now, if you want to calculate logarithm decrement, you have 2 pi. You are given the value of that guy, which is 0,0247 over root of 1 minus 0,0247 everything square. You have the logarithm decrement. Remember, the logarithm decrement is unitless. It's a constant. So don't worry about the calculation. You can calculate. You tap your calculator, you get your answer. But what I want us to do is to answer the remaining part of the question. This is very, very, very important. Determine the logarithm decrement. We did. Now, and the amplitude after 3 cycles of its initial displacement. Okay, again, there is also another formula, my brother, that says that logarithm decrement is equal to 1 over n, the ln of xn over xn plus 1. Now, what is xn? Xn is the initial position. You guys have done the practical. I'm pretty sure you've seen something like this. These waves were starting bigger and they keep reducing as you've seen something like this. Do you remember, guys?
Yes, sir.
If you did the practical. So this one here is the initial amplitude, the highest amplitude. Now they are asking after 3 cycles. So after 3 waves like this, let's say 1, 2, 3. After 3 waves like this, 3 is here. What is the displacement? What is this value here? That's basically what they're asking. So you are given the initial displacement, which is 3 in this case. Remember, you also have the value of the logarithm decrement that you will find here. So you want to solve. What do you want to solve? You have logarithm decrement to be 1 over 3, the ln of 3 over, I want to write xn plus n, but let me keep it x. And let me recall again, why am I writing like that? The n is coming from 3 cycles. The initial displacement is coming here, x, which is 3. That's the reason why you see 3, 3, 3 here. I was just recalling for you to see. Are we together? Now, Andile, what they want us to solve, they want us to solve for this x here. Now, it's just simple math. What do? We cross multiply here. We're going to have 3 times logarithm decrement to be equal ln of 3 over x. Remember this identity, guys. If you have e ln a, it gives you a. So if I want to drop this ln here, what do I need to do? I simply have to introduce e both sides. Are you with me, Andile?
Yes.
So what do we get? We get e 3 logarithm decrement to be equal to what? 3 over x. So what is x? X is 3 over exponential 3 logarithm decrement. So that's basically what was asked in this question. Any other? Do you have a question, my guys?
No, sir. On my side, no.
Angela?
No question.
Yeah. Do you guys have the strength so that we can close the link and send something else, or you want to call it a day for today?
Now I'm leaving.
You're leaving? Okay, it's fine. If you're leaving, I'll let you understand. How long is
Okay.
the short one?